see these in lectures, but here's one that I wish was true, but unfortunately it's not true. So the no theorem is that if you have a field and the polynomial ring and a binomial ideal in the polynomial ring, then I wish it was an intersection of primary binomial.
I'm sorry for stopping you. They are just
Yeah.
setting it up. I'm sorry. Okay, now you can restart because the recording was messed.
Okay, so my provocative title is how primary decompositions of binomial ideals and monoid congruences are wrong, and you should not do them, but you should do something else. And the something else I'm going to talk about. And I forgot to mention this is joint work with Ezra Miller at Duke University in the United States. It's been a couple of years since we did this, so we have a paper from 10 years ago. This paper came out, but it's still I'm still motivated by questions in this paper a lot. So I start with a no theorem. That is a statement that is not true but should be true. So if you have the polynomial ring over any field, then I wish that every binomial ideal had a primary decomposition into binomial ideals. So we could write it as an intersection of primary binomial ideals. Unfortunately, that's not true. We had the example already yesterday. So let me try this technology. So this is not true because x cubed minus 1 over q cannot be factored into binomials. The complete factorization is x minus 1 times x squared plus x plus 1. And only if you have a third root of unity, this second trinomial factor would split. Of course, there are theorems in this area. We know the original primary decomposition. If you leave out the requirement that you want binomial ideals, then every binomial ideal has some primary decomposition, like the one that we've seen on the handwriting, but it need not be into binomial ideals. So that's a very old theorem from the beginning of the 20th century. And in the end of the 20th century, Eisenbahn and Sturmfeld wrote a very influential paper on binomial ideals. The name of the paper is Binomial Ideals. And there they show that if you're working over an algebraically closed field, then the dream becomes true. Every binomial ideal is an intersection of primary binomial ideals. So both of these solutions are somewhat unsatisfactory. The first, because we lose the binomiality. The second, because we need to make this algebraically closedness assumption, which, if you think about applications, which is what we're interested in this school also, you would really like to talk about real numbers, about non-negative real numbers. Maybe the numbers mean probabilities or they mean concentrations of chemical species. So this algebraically closeness assumption can be a bit of a pain. And I personally also like computable fields, so like the rational numbers. I want to do something about the rational numbers. And so my talk is about a third way to fix the no theorem. Here's a quote from the paper that we also talked about yesterday. If you don't believe me, then maybe you'll believe the Fields medalists. So Bayer and Mumford write in their paper, if one has never done any calculations, one would be inclined to say, let's just always extend K so that we can factor polynomials or that our algebraic set splits. And already in that paper it says that's a very bad idea. And I think the explanation why it's a bad idea is because it destroys symmetry, it can destroy structure. So if we go back to x cubed minus 1, I would argue if you see x cubed minus 1 in a decomposition, you're basically done. You don't want to decompose it any further. If you decompose into x minus 1 times x squared plus x plus 1, you're breaking the symmetry. There's 3 roots of unity. They have like a nice symmetry. Why break it up into 1 that happens to be real and 2 that are not? It's like unnecessary. Or to quote Mumford, a bad idea. So what we're going to do is to exploit combinatorics. So the plan is to work with combinatorics because the coefficients cause us trouble. They need to be in an algebraically closed field. We get rid of the coefficients. So I want to talk quite a while about the combinatorial side of binomial ideals. And this is again about the exponents. And in this talk, we're gonna be slightly more general and talk about any commutative Noetherian monoid as our set of exponents. So you can always, for the entire talk, you can have your familiar example of n to the n in mind, which will give you the polynomial ring. But to develop the theory, it makes sense to make it more general, to work with an arbitrary commutative Noetherian monoid. Noetherian condition, in case you're wondering, is the same in this setting as finitely generated. And it can, so finitely generated is equivalent to this ascending chain condition on ideals. So these are very simple monoids. And monoid, of course, it has an identity, it has an addition, and addition is associative. Need not have losses. Yeah? Okay, so then we can make the monoid algebra. If we have, I already wrote this on the blackboard once. So you take one vector space dimension for each element of the monoid. That is how it looks as vector space. One monomial for each element of the monoid. We call it t to the q. And multiplication of monomials is addition of exponents, as you know. And in monoid algebras, you have binomial ideals, and a binomial ideal is an ideal generated by binomials. Okay, I allow arbitrary coefficients. In particular, I also allow zero coefficients again. And we want to work with these monoids instead of the whole algebra. So now we need to have the analog of an ideal, the analog, the combinatorial shadow of an ideal, the way to take a binomial ideal and forget all the coefficients that are causing us trouble is to consider these congruences. So very easy definition, I hope. A congruence on such a monoid is an equivalence relation that's compatible with the addition. So that means if A and B are equivalent, think of these graphs that we have been drawing yesterday. If A and B are equivalent, and I add the same thing, the same Q to both A and B, they stay equivalent. This is what I mean, compatible with the addition. And that is exactly basic algebra, the minimum requirement, so that the quotient modulus equivalence relation is again a monoid. Is an exercise. And when you have a binomial ideal in your monoid algebra, it gives you a congruence, and this green box here is how we forget the coefficients. From a binomial ideal, we forget the lambdas by considering only which exponents are in relation, and they are in relation if there exists some non-zero lambda such that t to the a minus lambda t to the b is an I. That's when A and B are congruent, under this congruent coming from the binomial ideal. And here we need a non-zero lambda, for then otherwise monomial ideals would cause trouble. You can check out why a non-zero lambda is necessary. Also, monomial ideals give us something. So if T in Q is a monoid ideal, yeah, what's a monoid ideal? It's something that's closed under addition with arbitrary monoid elements. Just this. And this corresponds to monomial ideals. Okay? And the congruence, we had this picture yesterday. I draw these, so I draw it like this for a monomial ideal. Let's say we have a monomial ideal generated by x squared and y squared. This is what we had yesterday. I drew this. Everybody is connected to everybody picture, like on the top right here, and that's the same happening here. And it has a name. It's called the Riesz congruence in monoid speak. Okay, monomial ideals correspond to this, like weirdly everybody is connected to everybody components, and binomial ideals make this nice picture. Okay, so there are some special congruences that we might need. The congruence with the fewest possible connections is the identity congruence, where there are no edges except from Q to Q for the same Q. Then the quotient is just the monoid itself. And on the other end of the spectrum, if I include all the edges, everybody is equivalent to everybody, then the quotient has only one element. So that's called the universal congruence. And we're going to intersect these congruences. So intersecting with the identity congruence deletes everything. Intersecting with the universal congruence does nothing. Okay, intersections of binomial ideals shall be compared to intersections of congruence. So note that I'm introducing new terminology, but I'm trying to make everything easier. There are no coefficients. There's only one operation now. There's only plus, and everything actually becomes easier. Here's something that might surprise you a bit compared to, say, group theory. If you have a homomorphism of monoids, that's just what you think it is, then its kernel is not a substructure. If you have a homomorphism of groups, the kernel is a subgroup. But here, because it's a monoid, we can do this argument, and we really, as the kernel, we really need to store all the pairs. If you have so if phi is a monoid homomorphism, yes. So phi from Q to Q prime preserves addition, then the kernel of that will be one of these congruences. You just store when two things are mapped to the same thing. We call that the kernel. And then turns out that by this gadget that every commutative Noetherian monoid is finitely generated, which means it is n to the n modulo one of these congruences. Okay, every monoid you see in this talk is n to the n modulo some of these congruences. One of these congruences. Okay, let's see some monoids. Here's N2. This is our favorite monoid, the mother of all monoids, as I call it. It's the mother of all monoids because every monoid is n to the n modulo congruence, every Noetherian. Okay, so then we have affine semigroups. These are finitely generated sub-monoids of Z to the D. And they appeared in toric algebra. So the presentations of these, of the semigroup algebra is a toric ideal. So this was the example of the matrix 1, 0, 1, 1, 1, 2. Remember, A equals this. And then you make a semigroup algebra, K, N, A. And that's my picture, this talk version of that example. Yeah, the 3 red dots generate a cone and a semigroup. And the presentation is by a toric. But you can have much more weird monoids. For instance, monoids can have these nil elements, which behave like infinity with respect to addition. So an element is called nil if adding it is absorbing. So Q is nil if Q plus A equals Q for any A. As it behaves like infinity with respect to addition. Infinity plus something is always infinity. And we call it nil. I mean, nil is on the sounds like 0, but there's a good reason for it to call it nil. Believe me for a moment, you would see the reason. Okay, so that can happen. You can have n natural numbers together with this nil, makes a perfectly fine monoid. Yes, the rules of addition are infinity plus something is infinity, and the natural numbers add as they add. So that's my picture for this monoid. This is in this setting. So this monoid on the left here, I call it the counting if you don't know many numbers monoid. It goes like this. So you have 0, 1, 2, and infinity. And 1 plus 1 is 2. And 1 plus 2 is infinity. Infinity plus infinity is infinity. 2 plus 2 is infinity. It's just like you don't know many numbers. Yeah, anything above 2 is like too big of a number to distinguish. So the congruence, you can already see it presented as a quotient here. It's natural numbers modulo. I call it 3 plus natural numbers. So everything 3 and above is in one congruence class. This is this notation. So I just take all the natural numbers that are above here, and by forming a congruence, I make them all infinity. Finitely generated abelian groups can appear. So this monoid on the right here, it has a torsion behavior. So there's the 0 here, and this purple dot here, if I add it to itself, I get back to 0. So there's a copy of Z modulo 2Z in the bottom here. Then there's another copy here, but it works like this. This purple dot plus this purple dot gets me back to this green dot. But this purple dot plus itself takes me back there, but also one up takes me to infinity. Okay, so such behavior, just remember that subgroups can happen. We can combine all of these. So this, there's a copy of N here, and then there's this subgroupy behavior, and then maybe we still don't know many numbers in this direction, infinity comes in. By the way, there can only be one infinity. So it's very easy proof, because infinity plus the other infinity must be the first infinity and also the other infinity, and so they're the same. But there can be two ones. So here's a monoid with two ones. So here's 0, then there's 1 and 1 prime, and then we go on. It's 2, 3, and so on. And 1 plus 1 prime is 2, and 1 prime plus 1 prime is 2, and 1 plus 1 is also 2, and all the other numbers behave as they behave. So this is also a possibility.
So in other words, you're saying nil as well, there is only one nil element.
Yes, so infinity and nil, yes, there's only one nil element, and I very suggestively always use this infinity symbol, but it's nil, I should call it nil. There can only be one nil, but there can be two of these one. I mean, one has no special meaning here, because the identity is 0. Yeah? So 0 is the identity in the monoid, because we do addition, we call it 0. Then we have this element nil with the infinity symbol, and then this happens to be the 1. Okay, so I can write out the congruences. Each of the pictures that I've shown you has a presentation by N2. That's good, we can make two-dimensional pictures, N2 modulo the congruence. So this is my slides version for this whole mess where everybody is connected to everybody. Yeah, so you take N to the N, N2, and you identify everything from the second layer on. And make it one class, so you get this absorbing behavior. Let's check that this is a congruence. If two things are congruent, let me get rid of the scribbling again. So if two things are congruent, like say these two dots, they are congruent. Now if I act with a monoid, I only go up and right. So the property of a congruence is if they are congruent and I go right, they stay congruent, and if I go up, they stay congruent. If I go down, of course, they don't stay congruent, but I can't go down because there's no addition goes up and to the right. Here's the presentation of the not many numbers monoid. I just identify here, 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 and then I have the big class representing the middle. Again, if these two things, oops, what happened now? I went a couple of slides ahead. Don't look at this, it's all secret. What happened? How did I do this even? Okay, here we are. So if these two are not congruent, if I move them up 3 times, they become congruent, but that's okay, yes? So the definition of congruent says if they're congruent, they stay congruent. And if they're not congruent, they can become congruent. And that's very important to find these locations where this happens. Okay, here's the Z2 behavior to make these classes that jump 2 steps. Okay, and so you can, addition and taking the quotient is compatible, yes? You can do addition. If you want to know how to do addition on the right here, you take any representatives and you do addition on the left. Yeah? If you want to know what this plus itself is, you take any representatives like this representative and this representative, you add them, so that's 1 plus 3 goes to 4, goes to green. That's why purple plus purple equals green. But if I do it here with the addition in N2, I land in the golden middle. Okay, this is the combination of the 3 behaviors, and look, it has to become more dense as I go up. Yeah, so it's not connected to the next neighbor, connected to the next neighbor, connected to everyone. That's how congruences work. And here's the double ones. So this has a green edge here, and it has the green edge has to be, if I move it up or right, it has to be there, and a purple edge, which also has to be there if I move it up or right. And so the classes look like this. Yes, we have these isolated dots here, and then one class for each degree, if I might call it this. Okay, so let's make the connection to binomial ideals. From congruences, we can also make binomial ideals. From binomial ideals, we can make congruences. And from congruences, we can make binomial ideals. And we can just choose unital binomial ideals. It's not unique, but here are some unital binomial ideals that give these congruences. So this nil behavior we make with a monomial ideal. This group-like behavior, it suffices to include one binomial, x squared minus 1, is this first green edge here, yes? X squared is the same as 1, is this first green edge. But if this green edge is there, then I can multiply this thing with x, which tells me x cubed is equal to x, and this is this purple edge. And multiply with x squared, which tells me this edge, or multiply with y, which tells me this edge, yeah? So these edges are all, this edge would be y times x squared minus 1. And it's of course in the ideal because it's an ideal. Okay, x minus 1 gives this next neighbor behavior. Here's the combination. So here we have y cubed for the nil, and then y squared times x minus 1 for this, and y times x squared minus 1 for this, and then nothing at the bottom. And here, one generator for the green edge, one generator for the purple edge. And so the whole spirit of this story is to, instead of doing things with binomial ideals, we want to work with these congruences. It's much easier, it's computing with pictures and combinatorics. Okay. Two more definitions we need. Well, there are also some more on the next slide. So an element is going to be called cancellative if adding that element is injective. I think it's very common notation in semigroup and monoid theory. Cancellative means you can cancel it. Yeah. So if A plus Q equals B plus Q, then A was already equal to B. I like to call it addition is injective. And we call it nilpotent if a multiple is nil. And there's this correspondence for monomials in the monoid algebra and monoid elements. So the cancellative ones are the non-zero divisors, and the nilpotent ones are, we need to invent a new algebra. I will not explain this. There's one subtlety with the nil in the algebra. We can maybe talk about it in the end. Okay, cancellative non-zero divisor, that's a good hint. So let's identify the nilpotents in our pictures. They are in the golden boxes, because remember the addition here, so these are actually all quotients of n2. So as long as you're not in the bottom layer, when you add things that are not in the bottom layer, you will always move up. And moving up means eventually you will land in the nil class. So everything that's in the golden box is nilpotent in each of these cases. The monoid on the bottom right has no nil, so it also has no nilpotent. Okay, so now we discovered in the course of this project, we thought, oh, there must be a theory of primary decomposition of congruences, and that will solve all our problems. So this was our dream at the beginning when the paper was like 4 pages. And then unfortunately it didn't work, but let me show you why. So, but the theory exists. From the 60s already, we get this theory of primary decomposition of congruences. And we thought this is the right thing to do, decompose binomial ideals, but it's more complicated as it turns out. So let's look at the bottom first. A congruence is a prime congruence if in the quotient every element is cancellative or nil. This is in formal analogy to a prime ideal. where in the quotient every element is a non-zero divisor or zero. Yes, this is just saying that the quotient is a domain, as you may have learned in commutative algebra class. And they continue they continue this analogy. It's primary if every element is either cancellative or nilpotent. Here it's nilpotent or non-zero divisor. While this nilpotent here refers to a power as zero. That's like the little subtlety that I'm brushing over. And irreducible is defined as you know it. If it's not the intersection of two strictly larger ideal, if it's not the intersection for congruences, we call it common refinement, but it's the intersection of the graphs of two strictly coarser congruences. And then you show exactly as Emmy Noether did that congruences have primary decomposition by first showing that they have irreducible decomposition using Noetherian induction, and then irreducible implies primary. Okay, congruences have primary decomposition. Great, problem solved, except not, because all these top left four pictures are primary quotients. All these congruences that lead to this are have the property that the non-nilpotents are cancellative. Here's a copy of N. Here the non-nilpotents are just one element group. Here it's a group is cancellative, and here it's N, it's also cancellative. So all four of these pictures are primary congruences, but my not very subtle color coding, if it was effective, should have shown you that this picture here really wants to be decomposed as an intersection of these three pictures. If I take the intersection of these graphs, I get this graph. There is a natural decomposition staring at us, and primary decomposition can't find it. Primary decomposition is too coarse to decompose this picture or decompose this binomial ideal if we then lifted two ideals. So that's the thing we want to fix. And this is not the only problem, there's another problem. While it's too coarse, it's also too fine. So in commutative ring theory, in primary decomposition, you know that primes are irreducible. If you have a prime ideal, say the zero ideal in the polynomial ring, you cannot write it as the intersection of larger ideals. So prime is intersection irreducible. And here it's not the case. It's like a really weird phenomenon. So when I discovered this example, I was like really surprised that they had accepted this primary decomposition in the 60s because it has this weird behavior. So if I take this yellow congruence, which identifies all the columns, and this blue congruence, which identifies all the rows, and I intersect them, I get nothing. I get the zero congruence. But the zero congruence is as prime as it gets. But it has this, the zero congruence has a non-trivial primary decomposition. It's really stupid. But what's going on? Let's say, what is the congruence of the yellow one? The congruence of the yellow one for binomial ideals, it's the congruence of y minus 1. Yeah, so that's, it says the yellow edge says y is the same as 1. And then copies of this to the right. And so the blue edge says x minus 1. And if I intersect those, then I get the product. I get xy minus x minus y plus 1. Oops, which parentheses am I using? Maybe these ones. No. So the reason is what's happening here is that this ideal, that's the intersection of these two ideals, contains no binomials. That's why in the combinatorial, on the combinatorial side, we don't see anything because the ideal intersection contains no binomials and therefore no edges. So the combinatorial version looks only at the binomial, so it can't see this phenomenon. Okay. These are the two things that happen, but we can fix them using a notion of mesoprimary congruences. So this word meso comes from, there's micro is very small, macro is very big, and meso means in the middle. And so this notion of mesoprimary will turn out to be in the middle of two primaries. it's finer than primary decomposition of congruences, but it's coarser than primary decomposition of ideals. And that's why it's in the middle of the two primaries. That's why we call it mesoprimary. Okay, so we need to make slightly refined definition. We call an element partly cancellative if either adding it is injective, so it's cancellative, or adding it leads to the nil. And we only require this for two A and B that differ by a cancellative. So in these pictures, differ by a cancellative, you should think are on the same horizontal level. All my pictures are made so that differing by a cancellative means being on the same horizontal level, yeah, on the same height. So for instance, this congruence over here is not mesoprimary because there's this element, the element Q is go one up, which takes these two elements that are not congruent. And if I go, let's take these two elements. And if I go one up, they become congruent. Okay, so I found this one element which is not partly cancellative. And the element that's not partly cancellative is go one up. And so what this expresses, a congruence is mesoprimary if in the quotient every element is partly cancellative. What this expresses is that all the non-nil classes look the same. Yeah, if you don't want to care about the technical details, mesoprimary congruence does exactly what we want. It sorts by combinatorial types. It's mesoprimary if all the non-nil classes look the same combinatorially. Now we have a theorem that says every congruence is the common refinement of mesoprimary congruences, and each of the components that is there witnesses a combinatorial feature, witnesses one of these behaviors of congruence classes in the original congruence. And now the thing you can do about this is you can prove that it's canonical. It's constructed from the picture in the sense that this picture here tells us what we need to do. We need to make one component for the isolated dots. We need to make one component for the green-purple behavior. We need to make one component for the blue behavior. So there will be three components, and the congruence will tell us which components to use. In that sense, it's canonical. We make no choices. There are no embedded components as in primary decomposition. There are no choices. It's canonical. The canonical one need not be irredundant. It can happen in special examples that the intersection is redundant, but we prefer, in this case, we preferred canonical over irredundant. It's a matter of how you make the definitions. I think in this paper, the most important results are the definitions. We've fought very hard, and the definitions were wrong many times. We had to correct the definitions many times. So most of the work we put in the definitions. Once the definitions were right, the proofs wrote themselves. So we started with the theorems. We know which theorems we wanted, and we know how we wanted to prove them. And the whole work, 5 years of work, was in finding the right definition. Okay. Yes. So the whole theory comes with all these gadgets that you know from primary decomposition. For instance, you find these components by having associated objects. So in primary decomposition in rings, you have associated prime ideals. We have a combinatorial version of that. We have associated mesoprimes, which isolate these combinatorial features. So to do this, to find these, we use localization, which is always very convenient to get things out of the way. So in monoid theory, it's also much easier than in ring theory because there are only finitely many prime ideals in the monoid. So if you localize at a prime ideal of the monoid, you basically just make some of the directions. If you think about n to the n, you make them invertible. Okay, you just make, instead of having, in this case, it's the x direction. In this picture, I make the x direction invertible. So now this picture just goes on in this direction. Localization means makes things invertible. And here, let's say I make the x direction invertible. And then to find these combinatorial features, I'm looking for pairs of elements that are joined when going in a non-invertible direction. In fact, in all non-invertible directions. So this prime ideal P has some directions which are now invertible. These are the ones that are not in P. And the non-invertible directions, I look for witnesses, which are two elements that are joined when going in a non-invertible direction.
Excuse me? So,
Yes.
so what do you mean by primeness here? Because everything is in the monoid setup, right?
So P is prime if when the sum is in, one of them is in. Yeah. If for all PQ in Q, P plus Q in P implies P in P or Q in P. But the much easier way to think about it is in terms of the faces of the monoid, is the complements of the faces. So there are finitely many prime ideals, and that for n to the n, there are 2 to the n prime ideals, and they just correspond to complements of the faces of the cone, which contains n to the n. So the
So how can you can we comment on this primeness by looking at the binomial ideal from the starting?
so the monoid prime ideals correspond to the
It seems to be the definition is really depending on the monoid you are taking, right?
yes, but I can make the definition in n to the n, so modulo the congruence. So
my point is that this is possible that regarding to one particular setup, you have the primeness, but if you change your monoid, the same P may lose its primeness. Am I right?
no, by going to a congruence, it stays prime.
It stays prime. So either
Yes.
the congruence changes, because the definition is really depending on the congruence, which is coming through the generators of the binomial. So I was just skeptical about the universality of the primeness.
Let me maybe switch here and make one way to show you one way to think about this. So if Q is n to the n, then monoid primes P are one-to-one with ideals generated by variables. Ideals generated by variables. So it starts with the empty ideal. So the monoid ideals are the empty ideal, the one generated by E1, and so on, and the one generated by E1 to En, and they correspond to the zero ideal, the ideal generated by X. So this is here in Q, and here it's in K to the Q. And so if you take Q equals to Q, you take all of those and you take their you take those ideals modulo the congruence. Yeah, so Q is equal n to the n modulo a congruence by the general structure theorem. So you can just take the primes and they stay prime.
Oh, okay, got it.
And it's even better. So if you think about the affine semigroups that are contained in a cone, they also correspond to the complements of the faces. Yeah, so there's also some geometric way to think about these. But they really correspond to monomial prime ideals. And monomial prime ideals.
In fact, you were defining the whole new dictionary for the primary ideal. So then there stays a question how the things go for the prime. So I was just expecting probably you are going to change the definition of primeness as well.
Wait, wasn't there prime? You mean monoid prime ideal?
Yeah.
That's a bit dangerous. There's prime congruence and prime ideal. Okay,
Okay.
so prime is different. Prime congruence and prime ideal. So monoid ideals correspond to monomial ideals in the ring situation. Monoid congruences correspond to binomial ideals. But monomial ideals can also give congruences, but these congruences look like you take a monoid ideal and identify everybody to everybody.
Okay.
Okay, now with the localization, I'm talking about the prime ideals of the monoid. And the way to think about it is you make some of the directions invertible. It's a technical gadget. I think it will help to see an example how to do this. So the witnesses are the ones that are joined by going in the prime direction. So then we can define this notion of an associated prime congruence. A congruence is prime. As a reminder, if in the quotient everything is nil or cancellative. And a prime congruence is associated essentially if its non-nil elements, the ones here, look like these unique classes that you have in the mesoprimary congruence. Yeah, mesoprimary was defined so all the non-nil classes look the same, and the prime congruence is just stores one copy of this. And then you have a theorem like mesoprimary if and only if it has a unique associated prime congruence, like primary if and only if it has a unique associated prime. That's almost the definition. It is the definition. But here we have it as a theorem. We made the definition so that this is clear. Okay, so there's an algorithm that works with these witnesses. I think I will explain it in an example. So how do we find a decomposition? So we haven't seen the decomposition of this picture. So what does the algorithm do to find the mesoprimary decomposition of this congruence? This is not even primary. Yeah? This was the one that's not even primary, or decompose this idea. So first, we have to search through all the localizations. So if we make both directions invertible, we make this invertible and this invertible, then suddenly I can move this purple edge down and I can move this green edge over, and I can get this picture. Now I need to search for witnesses, but I need to search for witnesses outside of the prime ideals that's generated by the generators of the monoid. So it's all set up so that I now have to do something. I have to check a condition. This is for all elements in the empty set something, so it's just true. So this is one of the components which I get from making both directions invertible. If I make only one direction invertible, I also get this picture, except that this purple edge is not there, but it doesn't matter. But now I need to search for witnesses, things that when adding them join two things, and now I can't find anything. So for making one direction invertible, I get nothing. I get no witnesses of like non-additive and non-injective additions. I don't get anything. Then I go to the last case, I make nothing invertible. If I make nothing invertible, I have these two witnesses. If I move them right, they are joined. If I move them up, they are joined. And now I make one component for each witness. And the algorithm is like this. I take this thing. I consider the poset in divisibility below it. This I preserve. And everything else I make nil, which gives me this component. I introduce a new nil. I make everything not below this one element, this witness nil. And I get a second component where I do it for the other witness. Okay, and that's the algorithm. Let's go back. You have to find all these witnesses, which are pairs of a prime and an element. You make one component for each witness by doing this thing, localize. The localized quotient is partially ordered. You have to show something. And then you make every class below the witness look like a witness. This part we didn't see. So you copy the behavior downstairs. It will be in the next example. And every class that's not below, you make nil. We call it the co-principal component, and the intersection of co-principal components gives you the original congruence. So that's meso-primary decomposition. We can remove some redundancy by restricting to a notion that's called key witnesses. So if you read this paper, I think I could also give a talk in the law school. So there are key witnesses, eyewitnesses, false witnesses, there are all sorts of witnesses in this paper. So later we also have false witnesses. That's very dangerous.
Thomas, can you explain the middle picture once again? Because I didn't get that XY scale in the previous one. Yeah, the middle one.
Yeah.
How X and Y scale is coming up, showing up.
Okay, I'm doing a combinatorial procedure, and I'm writing the binomial ideals below to guide your intuition. Okay? So the combinatorial procedure that I do is I identified these two witnesses. Why are they witnesses? Because these two elements, when I go up, they are joined, and when I go right, they are joined. That makes them witnesses for a combinatorial change. They show me that something changes in the direction. And my recipe tells me I need to have one component for each witness. That's why we are at the moment constructing these two components. Then the algorithm tells me you go to your witness and you look in the addition pose set of the monoid. So each monoid is a pose set, partially ordered set with respect to addition. Yeah, so addition moves you further into the monoid and you can go back. So I look everything that's not below it and everything that's below it. The stuff that's below it is in this case only the identity. I keep that. And everything that's not below it, I make it nil by connecting everybody to everybody else. So to make this component, I take this one witness, and everything that's not below it, I connect everybody to everybody else. Here I use this gold notation. It's just a.
What is wrong if one takes X and Y instead of XY scale?
X and Y instead of XY squared will be not radical. So this will be a radical. So this idea is not radical, and then the intersection. It will give a different ideal. But so when we go into so as soon as you go into actual ideals, you have this problem that primary decomposition is not unique. The embedded components, they are not unique. Yes. So the problem will be that on the binomial side, you can make choices. And I want here a canonical decomposition that's forced upon me from the congruence. So I will make this decomposition, and it is redundant. So this one is redundant. I think if I remember correctly, if you intersect 2, you're done. It suffices to intersect 2. But the mesoprimary decomposition should be canonical, so I will just not break the symmetry and take all 3 of them.
Okay.
Okay. We also fix this problem because there are just no witnesses here. So this has, in terms of mesoprimary decomposition, this is mesoprime and there's nothing to decompose. No witnesses. The canonical decomposition of this is just this, no decomposition. So this other problem with primary decomposition is also fixed. So now the miracle appears. If your congruence comes from a binomial ideal, the decomposition can be lifted back to binomial ideals. So the decomposition so the principle would be you take your binomial ideal with coefficients, you extract the congruence, then you decompose the congruence, you compute all the witnesses, and then there's a way, the ideal tells you how to fill in the coefficients for the components. You can read it off from your ideal how to fill in the coefficients in the components, how to make the binomials, what kind of coefficients are. And in particular, this will work over the original field. We don't extend the field. It works over the original field. The ideal just tells us which coefficients to pick. And so we have the theorem that K be any field, and that's now my third alternative for the no theorem. Every binomial ideal has a decomposition into mesoprimary binomial ideals. Mesoprimary binomial ideals need not be primary. It's not primary decomposition. I argue it's better. It's the right decomposition for binomial ideal. And each of the components has to be there because it witnesses a combinatorial or arithmetic feature of I. Okay, so I'm almost done. Yeah, this is what I said. You determine the witnesses of this congruence and you construct the co-principal components which inherit their coefficients from I. And you decompose. So now there are all these witnesses, and some of them are necessary, not necessary for the congruence. Some of them are not necessary for the ideal. So there's many subtleties. That's why the paper is relatively long. And we defined this class of character witnesses, which are the ones that are necessary for the ideal decomposition. And you have to take care of all these subtleties, like ideals that whose intersection is not binomial, and ideals whose intersection should not be binomial but is. Yes, so if you intersect z minus 1 and z plus 1, you get z squared minus 1, which is kind of a bug, because if z minus 1 intersected z minus 1, yeah, I can draw this picture. So if you have this here, this intersection here gives z squared plus 1, and this intersection here gives just z minus 1. But all the congruences for all the 4 ideals are the same. Yeah, these are all the congruences. There's just one is the identity is connected the one to the one next to it. So there's the phenomena that the decomposition of congruences can see, and this is abstracted in this notion of false witnesses. But it can be fixed. Okay, so there were some questions that could be resolved with this. So one question that was in algebraic in Eisenbach-Sturmfeld was about irreducible decomposition of binomial ideals. So this now refers to irreducible decomposition of ideals. So ideals that cannot be written as the intersection of strictly larger ideals. Is that closed under binomialness? And the answer is no. And so this example, I think that I studied the properties of this example, I think in 2009, but only in 2014 we discovered that it's a counterexample to this conjecture. I mean, it also requires a proof, which was a bit complicated and required all the theory, but it's funny that the example is actually relatively simple. So that's a paper that's joined with Chris O'Neill and Ezra Miller. But I think there are many open problems about binomial ideals left, and in particular, you know that I like algorithms. So the upshot of this, so why I did this, is that I wrote this binomials package for Macaulay 2. So if in Macaulay 2 you decompose a binomial ideal, you use a software that I wrote during my PhD. And when you type this ideal in, x to the 17 minus 1, and y squared, I don't know why the y squared is there, it will actually construct a field extension, cyclotomic field, which contains 17th root of unity, and will give you this output. And what do you prefer? If you're in your application, you're at this point, and it's x to the 17 minus 1, and you type decompose, and it does this. So which output do you prefer? Do you prefer your computer algorithm to stop here, or do you prefer this actual decomposition over a field extension? And this goes back to this Mumford. And this is mesoprimary decomposition is not implemented because theoretical problems have to be solved. The algorithmic computer science problems have to be solved. How to efficiently decide if when you have 2 ideals, the intersection of their congruences is empty. This is the first starter problem. So if somebody wants to work on that, how to make an efficient algorithm to decide that, I could certainly help them get started. And then eventually we'll have a computer software that stops here and tells us, okay, the rest of the, now you know everything because you know the 17th root of unity, and I don't need to write them as WW17 to the 14 for you. Okay, thank you very much.
Any question?
I have a question. How do you made this from congruence to the ideal? I do not understand how
Yes.
you get.
Okay, so
If you can
to,
give me
to
an
go
example.
from a congruence to an ideal, you make the unital, so you have your congruence, and formally you can just write t to the a minus, and I just as a coefficient I just put 1. I just write my t to the b whenever a is congruent to b. Okay, now that's a very infinite generating set. So to find a finite generating set of this, you need to somehow find finite generators of the congruence. So if you think about the graph, you need to find a finite set of edges so that every edge in the congruence arises from right translation and up translation from that. So it's also not clear to me, there must be some variant of Gröbner basis algorithm that terminates in finding this generating set. Maybe it's even easier, but I mean, the fundamental question is already, what's the data structure? How do you store a congruence in the computer? If you want to store it, you need to find this finite generating set, like with ideals. Yeah, we store ideal by giving generators.
If we index something according to binomial or monomial, so the decomposition thing also cannot be applied to that indexing function. For example, if I have a persistent module indexed by monomial or binomial, so if monoid and binomial can be decomposed, the same way the functor, the persistent module can be decomposed.
Chris O'Neill, whom I mentioned, extended this theory to monoid modules. Okay, so maybe this could be something in this direction. So if you have some set on which the monoid acts it acts as in terms of action, then you can also have a mesoprimary decomposition of this structure. So this is something that Chris O'Neill developed in a follow-up paper. I can find the reference for you. Maybe this goes in this direction.
Yes.
I mean by index. So the bigger picture in which this fits, I think, is multi-graded algebra.
Yes,
so you have modules graded by monoids, and I think this is the next step is to look at these mesoprimary decomposition of monoid modules.
Thank you.
Thomas, can you please share the reference of your paper with Miller?
Yes. So it's in algebra and number theory. It's called Decompositions of Commutative Monoid Congruences. And binomial ideals. And I can also, I don't know, include it in some. It should be cited in my references also in the PDF, but note it's from 2014 or 15. So let me check on my on the Chimpa webpage. KM14, whether reference KM14 is the notes, but I think so.
Thank you.
Thomas?
Yes.
I have a question. What about the Gröbner basis of these binomial ideals?
Sorry, which ideas? I didn't get it fully.
Gröbner basis of these binomial ideals.
Gröbner basis.
Is it defined?
Gröbner basis for, maybe she's asking Gröbner basis for congruences.
Gröbner basis for congruences, I don't know. Should be possible to once one wants to make these data structures and make these algorithms actually work, I I think it might be useful to, because this is already implemented, to always work with unital binomial ideals. So when you want to store a congruence, you don't store the congruence, but you make the unital binomial ideal and work with that, the one that I write down here. And then that might be the way to go, but I'm undecided on that. And yeah, I mean, variants of Grübner-based algorithms will often be necessary if you have something that's, if you want to make a finiteness condition such as Noetherianity effective. I mean, this whole class of Grübner algorithms makes it actually terminate when the theory says, well, the chain stabilizes, but when, yes.
Can I get a question now? There's that. Yes, there's an announcement. I have emailed you every month, so by now you have received my email about that tool. So it's in a,
So it's a detailed email, so you can check your emails, please. And so we have the tour that will start from 3:30 till 9:30. So we'll be here by 9:30 most probably. And we'll have